Today's lecture is on fertigation. Fertigation is the joint application of water and nutrients to the crop. It's a very nice idea because we're gonna put water and nutrients where the crop can uptake them. Of course, to do that right, we will require a dosing system for the nutrients to put the nutrients into the irrigation water, and therefore it requires a more or less sophisticated irrigation system. So it will be mostly suitable for drip irrigation, although it can be used for other types of irrigation systems like a sprinkler or even irrigation machines. Even in some occasions we can use it with surface irrigation. The idea behind fertigation is that we will be improving the efficiency of the nutrient application, because if we localize the nutrients, we will have areas of the soil with a high nutrient concentration, so we will saturate the cation exchange capacity of the soil, so we will have a high nutrient level in the soil solution. So in poor soils or high fixing capacity soils, it will be better to use fertigation. Also, we have more efficiency because we put the nutrients where the roots are, not in other parts of the soil. Furthermore, as the water content in the irrigated areas, in the wet bulbs, is high, we will have better conditions for the transport of nutrients from the soil to the root, because many nutrients flow with the water uptake. We have also an advantage in the use of fertigation, because as we are applying the nutrients very frequently, the nutrient concentration will not be too high at a specific moment, so we can match the demand of the crop with the supply of the nutrients. Therefore, we will be reducing the losses of nitrogen, and we will increase the absorption and reduce the precipitation of phosphorus. In this graph, you see the total uptake of nitrogen of a crop. This would be this sigmoid curve, shows the cumulative nitrogen uptake by the crop, and the dotted line shows the soil available nitrogen. In conventional fertilization, we apply nitrogen, say, 2-3 times during the whole cropping season. So we will have huge increases in the concentration and then a decrease following the uptake by the crop. But there is a huge variation, so we will have here low concentration, but then we will have here a very high concentration. So the nutrient supply from the soil will be changing through the growing season. That leads to times during the year where we have an excess of nutrients in the soil that can lead to nitrogen losses. These are these areas that are shown here. If we apply fertigation, the variation in the nutrient concentration in the soil, in this case of nitrogen, is rather small. We have only this variation. And that will mean that we will never have these high values of nitrogen concentration in the soil that could lead to huge losses of nitrogen. As I said before, we can even apply fertigation even with surface irrigation. This is an example of a tank that is added to apply fertilizer in a furrow irrigated tomato crop. This is a general view of the crop. This is close to harvest, and this is the plastocanal pipe that is used to supply water to the different furrows. Then we have here to the left, not seen, we have the tank where the farmer puts the fertilizers and dissolve them with water to be entering into this pipe. Okay, this is a very simple solution to put fertilizer into a furrow irrigated crop. There are more sophisticated systems for fertigation. In general, we distinguish two general types of dosing systems. The first is the proportional, and the proportional tries to put a constant concentration of nutrients into irrigation water. Therefore, we use a device that will be injecting nutrients in proportion to the water flow. This is a proportional system. This is the best system because we can fix the concentration of nutrients in the irrigation water solution. On the other hand, a less sophisticated alternative is the quantitative. For instance, the example that we have seen before for tomato is a quantitative system because the farmer puts a known amount of nutrients into the tank and then he will be adding water. If you think about it, the concentration of nutrients will be changing during the irrigation. First, you will have a high concentration, but at the end of the irrigation, the nutrient concentration will have decreased. Quantitative means that the total quantity of nutrients is fixed, but the concentration changes. Okay, if we perform proportional dosing of nutrients, we can use different alternatives. And here we have three possible alternatives for injecting nutrients into the irrigation system. The differential pressure uses the difference in water pressure between the two sides connected to the tank, to the fertilizer solution tank, and due to the difference in pressure, there will be a flow of water crossing this tank and flushing nutrients into the irrigation system. Here we have the symbol for a non-return valve, which is very important. In general, all fertigation systems will have non-return valves to avoid nutrients going into the pump that could lead to corrosion, which is undesirable. And we can regulate the entry, the flux of nutrients into the water by operating on these valves. Okay? So, if you think about it, this does not require additional energy to operate. It's using the energy of water to get the nutrients into the main irrigation line. The same happens with a venturi. In a venturi, we create a depression by this narrowing of the pipe. This is called a venturi, and this is connected to the fertilizer solution tank. As we have here a depression, it will take up fertilizer solution and inject it into the main irrigation line. Here we have also a non-return valve before upwards from the venturi. Here we are also using the energy of water to take the nutrients into the irrigation system. In the case of an injection pump, we require additional energy to operate the pump, because we are using a pump that will take up water from the main line. It will take also the water from the fertilizer solution and put them back and put the mixture into the main irrigation line. Here we have a non-return valve. So in these two cases we don't need additional energy. In this case we will. This is more accurate because this will not depend on the pressure of the irrigation system. But here and here we are depending on having good pressure at the irrigation system. If we have problems with pressure, then the venturi or the differential pressure will not be working correctly. So this is the most accurate system for injecting fertilizer into the irrigation system using injection pumps. If we think about fertigation, we can think about quite a range of possibilities. The extreme possibility is applying to the crop a complete nutrient solution. And that will be required in the case of hydroponics or artificial mediums, for instance, perlite, where we need to put all the nutrients to the solution. In general, that requires several fertilizer tanks. For instance, the separation of nutrients between the tanks can have different alternatives, but one alternative is putting in one tank all macronutrients except for calcium in an acid medium, applying part of nitrogen or phosphorus as nitric or phosphoric acid. That will create the acid medium. This would be nitric acid or hyperphosphoric acid. And the second tank will have fertilizers with calcium in a neutral or acid medium. But sometimes we can have 3 different tanks. In some huge irrigation systems, we can have more than 3. In some cases, people would put each fertilizer on a separate tank if the installation is large enough.
And micronutrients?
Micronutrients would be, I think that on tank B. Yeah, these are other alternatives. For instance, tank A with well, you can have micronutrients on a separate tank, like in that example, tank A micronutrients, like in the case before, tank B fertilizers, and tank C micronutrients. But in some cases you can put the micronutrients on tank B along with sulfates, phosphates, and potassium nitrate. In general, potassium nitrate can go in either of the tanks. And very importantly, iron would go to tank A, not to tank B with the other micronutrients, to avoid having iron and phosphates or sulfates in the same tank. In general, this is related to the production of insoluble forms that would precipitate. That's what we need to avoid. So in the mixture, we try to make combinations that do not create precipitates that would be clogging our irrigation system. Well, that was, let's say, the most complex situation where we need to put everything into the irrigation system, all nutrients. But in many cases, we only need to apply part of the nutrients with fertigation. And one simple alternative is putting phosphorus, because phosphorus is the most complex of all in terms of insoluble compounds associated to phosphorus. So we put phosphorus as basal fertilizer, we add it to the soil before the crop, and then we will be adding nitrogen and potassium by fertigation. And in this case, we only need one tank to do fertigation. Okay. The main properties that have to be considered for fertilizers used in fertigation are, of course, the nutrient concentration, but in this case, the purity, the absence of impurities is very important. Of course, the solubility, because the solubility will mark what is the maximum concentration that we can keep in the stock solutions. We will talk about stock solutions later. What is the pH effect and the compatibility? The compatibility means if we can mix two fertilizers in the same tank. In principle, the pH of the solution should be close to neutral, slightly acid, from 5 to 6.5. We want to avoid root damage, but also, very important, we want to avoid precipitation that would occur under basic conditions. In general, it is advisable to have some ammonium in the solution. From 10 to 20% of the total nitrogen should be applied as ammonium. But if you only apply nitrate, there is no problem. Mostly if you are doing incomplete solutions, if you are applying nitrogen and potassium, and you are applying phosphorus, if you are doing fertigation on crops on soil, it's no matter if you apply only nitrate or you apply more than 20% of ammonium, because ammonium will be converted to nitrate by nitrification. The solubility of the fertilizers will increase with temperature, so we can have problems of low solubility when the temperatures are low. And for some products, there is a reduction, an important reduction in temperatures during the dissolution. For instance, urea can create a very low temperature while you are dissolving urea in water. That might cause problems with solubility of other compounds. If you are trying to dissolve urea and you mix it with other products, you can have problems with that. Okay, here we have a list with the main fertilizers used for fertigation. You see monoammonium phosphate. So we have complex fertilizers like monoammonium phosphate or monopotassium phosphate. In the first, we have phosphorus and nitrogen. The second has potassium and phosphorus. Very commonly use ammonium nitrate, which has the two types of nitrogen. And ammonium sulfate is also quite common. And then we have nitrates, calcium, potassium, magnesium. Then we have potassium chloride and potassium sulfate are the two soluble fertilizers, straight fertilizers for potassium. So if we want only to apply potassium, we would choose between potassium chloride and potassium sulfate. What would be the advantage or disadvantage of potassium chloride versus potassium sulfate? Any idea? Potassium chloride would not be advisable under conditions of high salinity, and potassium sulfate would help in those crops that might require more sulfur, like some brassicas. Okay, in the list we have also the acids, the phosphoric acid 55% or phosphoric acid 75%. We have also nitric acid, and then and then the anhydrous forms of calcium nitrate and magnesium nitrate. In this table you have the equivalent weights in grams per equivalent. These are important because the calculations of the solutions many times are performed considering the number of equivalents that you need for each of the elements, and then you need to convert that to mass of the product. We have also the solubility at 20 degrees. There is a huge variation in solubilities in kilograms per cubic meter, and then we have the concentration for NPK, S, calcium and magnesium. Note that the concentrations are all expressed as percentage of the elemental form. In other words, this is for phosphorus, but not P2O5, which is a very commonly used unit, and this is potassium K and not K2O, which is commonly used. People also use calcium O, oxidum of calcium, or oxide of magnesium. Remember, this is related to elemental form. Okay? So, using this information that you have in the book, you can convert any amount of the element into amounts of the corresponding fertilizer that you need to put into the system. Okay. One thing that is important is that some of these fertilizers are also, some of these solid fertilizers are also used for normal fertilization. But the industry produces solid fertilizers with higher levels of quality in terms of purity than those used for normal solid fertilization. Purity is important because the impurities might create problems of clogging of the drip emitters in drip irrigation. The industry also produces commercial solutions which are rather expensive, but makes things easier for the farmer because you buy something that you need only to put into the irrigation system, into the fertigation tanks directly. They also can provide composite liquid fertilizer solutions. In general, the problem with that is that they are rather expensive and the concentration of NPK is rather low. So, the most economic solution is to buy high-grade solid fertilizer from the industry and then do the mixing and the dissolution in the field, in the farm. As we said before, the incompatibility has to do with the risk of precipitation of calcium and magnesium compounds. Basically, So we say that two products are incompatible when we cannot mix them in the same tank. For instance, calcium nitrate will be incompatible with phosphates and sulfates because precipitates of calcium sulfate or calcium phosphate will form. The same occurs with ammonium phosphate when combined with magnesium sulfate, because then we will have magnesium phosphate that will precipitate. In the case of micronutrients, we have to be very careful in terms of the pH and the possible incompatibility with other cations. Well, you have already seen the control of salinity, and you can remember that that water in general contains salts, and the main salts that we can find in water are chlorides, sulfates, carbonates, and bicarbonates of the main cations, which are calcium, magnesium, sodium, potassium. We have to be especially careful with bicarbonate, because bicarbonate will combine with calcium and magnesium and will precipitate with high pH. Even having only more than 2 milliequivalent per liter will be a problem. To avoid that problem of formation of precipitates, we need to add acid, correct the pH of the solution. Also, it will be interesting to consider nitrate as the main source of nitrogen. We will see later how can we can calculate the acid correction depending on the quality of your water. Other problems that may occur related to water quality or the conditions of the water that are our main supply is the presence of algae and bacteria in irrigation reservoirs that would require treatments like chlorine, copper sulfide, or potassium permanganate. Algae and bacteria not only, algae promote the presence of bacteria, so it is important to remove algae, but algae also produce clogging of the irrigation elements, so we don't want algae at all in our system. In the case of ferruginous water, we can have problems of deposits of iron or manganese when they oxidize, and that is more complicated to deal with because it requires aeration or chelation. So you can aerate the water or add a chelate agent, and then you need to precipitate to filtrate the precipitated oxides. So, but it is a more complex situation. This is not as common as the presence of bicarbonates. As we said, the precipitates have the problem of clogging the emitters, and the main problem is related with phosphorus. That is why it is simpler to put phosphorus before the crop as a basal fertilizer and then add only with fertigation nitrogen and potassium. The problem with phosphorus will occur in alkaline waters with calcium and magnesium because of the production of phosphates of calcium and magnesium, and that requires the use of acid phosphorus fertilizers. We have already mentioned phosphoric acid and monoammonium phosphate. We can also use some acids after the irrigation season to unclog the drippers. And it is always very useful to use fertigation times smaller than irrigation times. So during some time, at the end of the irrigation, we will be only putting water into the, let's say, pure water into the irrigation system. That will be flushing any possible nutrients that are left in the pipes. Okay, let's see now how to calculate the so-called stock solutions. So what we do is that in the fertigation tank we will create a concentrated solution. This is called the stock or mother solution. In Spanish is solución madre. So in that tank we create this concentrated solution, and we will be adding a given amount of that solution to a given amount, greater amount of course, of water in the irrigation system. So we will be diluting this stock solution to create the irrigation water that will be reaching the crop. The ratio between the concentration in the stock solution and the concentration in the irrigation water, this concentration factor can go from, let's say, 1 to 100 to 1 to 300 typically. Could be even much higher depending on conditions, but it is safe not to go too high, because we can start to have problems of precipitates if this ratio is too high. To calculate the stock solution, we can start from two different situations. One is that the total nutrient to add is known, or the other possibility is that the optimum concentration in the fertilizer solution is known. In other words, the second case is when we know the recipe. We know that we need to have the concentration of nitrogen like that, the phosphorus that, and so on so. Let's consider the first case, when we know what is the total amount that we need to add. It's the simplest situation, and in this case we are only considering fertigation with nitrogen and potassium. We assume that we are applying phosphorus as a basal fertilizer directly to the soil. So let's consider a citrus orchard requiring 200 kilograms of nitrogen per hectare and 270 kilograms of potassium per hectare, with a total seasonal irrigation of 500 millimeters. And we want to calculate a stock solution with a dilution of 200 times. Okay, well, if we want to apply only nitrogen and potassium, let's start using with a fertilizer product that has both, like potassium nitrate. Potassium nitrate has 13.4% of nitrogen and 39% of potassium. Let's start by calculating how much we would need of this product if we wanted to supply the whole requirements of potassium or nitrogen using only potassium nitrate. So if we need 270 kilograms of potassium per hectare, we divide that by the concentration of potassium in the product, which is 39%. So we divide 270 by 0.39, we come up with 692 kilograms of potassium nitrate per hectare. If we wanted to supply the whole needs of nitrogen, we would divide 200 kilograms of nitrogen per hectare divided by 0.134 kilograms of nitrogen per kilogram of potassium nitrate. That gives 1,493 kilograms of potassium nitrate per hectare. We take the smaller value, 692. We take 692, and with 692 we are applying, we multiply by the concentration of nitrogen in this product, and we are applying 92.8 kilograms of nitrogen per hectare. So applying 692, we are meeting the whole demand of potassium, right? And we are meeting part of the demand of nitrogen. Now we will need some more nitrogen. We calculate how much nitrogen is left to supply to the crop. We subtract 200 minus 92.8, which is the nitrogen that comes with this amount of potassium nitrate, and we come up with 107 kilograms of nitrogen per hectare. We could complete this amount of nitrogen, for instance, using urea. So we divide 107 kilograms of nitrogen per hectare, we divide by the concentration of nitrogen in urea, and we arrive to 233 kilograms of urea per hectare. So we would need to apply 692 kilograms of potassium nitrate per hectare plus 233 kilograms of urea. Now, as we need to apply 500 millimeters of water during the whole growing season, we simply divide the total amount of potassium nitrate by 5,000 cubic meter, because this is kilograms of potassium nitrate per hectare. 500 millimeters is 5,000 cubic meters per hectare. So dividing this by this, we come up with the concentration that we will require in the irrigation water, 138.4 grams of potassium nitrate per cubic meter. And dividing the total amount of urea by the total amount of water, we come up with 46.6 grams of urea per cubic meter of water, of irrigation water. But we said, no, we are not storing irrigation water with the potassium nitrate and urea added. No, we are storing a concentrated solution. As we said, we want to do a 200 times dilution to get this concentrated, this stock solution. So we multiply these values by 200, and we come up 200 multiplied by 138.4, we come up with 27.68 kilograms of potassium nitrate per cubic meter of stock solution. The same goes for urea. We come up with 9.32 kilograms of urea per cubic meter. This would be the amounts that we would put into the fertigation tank. But remember, this is a concentrated solution. This is the so-called stock solution, which will be mixed. Each liter of stock solution will be mixed with 199 liters of clean water to get the final irrigation water that will be reaching our crop. Okay, that was the simplest case that we can imagine, because we are only considering, we know how much is the total amount of nutrients that we need for the whole growing season, but also because we only are considering nitrogen and potassium. The most complex situation is when we need to apply all the nutrients required by the crop. That was the second alternative that we were talking about, when the concentration of the different nutrients is known. In this case, we will try to produce a solution that is assumed to be good in general for plants. It's the so-called the Hoagland and Arnon solution. The Hoagland and Arnon is defined by a set of concentrations. And this is the Hoagland and Arnon is, here is marked as ideal, 14 milliequivalent per liters of nitrate, 1 of phosphate, 4 of sulfate, 0 of bicarbonate, 0 of chloride, 1 ammonium, 6 potassium, 8 calcium, 4 magnesium, and 0 sodium. This is, if we have pure water, simply by putting there these different anions and cations, we would have, let's say, the best combination to feed our plants with a hydroponic solution. Okay? But in many cases, we never have in nature pure water unless we are collecting rainwater. But this is not usually the case. Usually we are taking water from a surface reservoir, or we are pumping from a well. So this water will have salts, and we have to consider the presence of those salts when calculating the amount of nutrients that we have to put into the solution. In this example, we have a water that is like this. We have a water with no nitrate, 0 phosphate and sulfate, 2 of sulfate, 2 milliequivalents per liter, 2.5 bicarbonate, 1 of chloride, 2 of calcium, and 2 of magnesium, and also some sodium, 1.5. So the addition that we would need would be, to get the ideal solution, would be, we need to add, if the water has no nitrate and we need 14, we need to add 14, right? For phosphate, we would need to add 1, and so on. 2 for sulfate, -2 for bicarbonate. What is the meaning of -2? Well, -2 means that we will be neutralizing using an acid. And in general, to produce a Hoagland and Arnon, we will use nitric acid. So we will be adding 2 protons to leave some of the bicarbonate not neutralized. We will leave something like 0.5 not neutralized. Then for chloride, we have 1, but the ideal is 0. We add nothing. But the final solution will have chloride. So in reality, the final solution, unless we start from pure water, from the ionized water, we will have something that is not exactly the ideal Hoagland and Arnon solution. So for ammonium we will add, for potassium we will add the 6 milliequivalents, for calcium only 6 are required, for magnesium only 2 are required, and for sodium we will have in the end 1.5, which is not desired in the ideal solution. Once we have calculated the addition like this, we will write this type of table where we put a column, and well, in the row we write the different cations, and in the column we write the different anions. The cations, ammonium, potassium, calcium, magnesium, and protons. And here we write nitrate, phosphate, and sulfate. And we put here the totals that we need, the totals that come from addition. For instance, for total nitrate, we put here 14. Why? Because in addition we have 14. For phosphate, we go to total phosphate, we need 1. For total sulfate, we need 2. And now, coming in this direction, we do the same according to the total ammonium that we need to add is 1. We put here 1. The total potassium is 6. Calcium 6. Potassium, calcium 6. Magnesium, we need to add 2. And protons, we said that we needed to add 2 protons, right? Okay. Now, so we have started by putting here the totals, okay? And now we need to fill the values inside this table. And we start by adding the protons as nitric acid. So nitric acid is this and this, acid and nitric. And here we write 2 because we are adding 2 milliequivalents of nitric acid. So we write here 2. We start doing this, and then we fill the row of nitrate in the order first calcium and calcium. What do we need for calcium? We need 6, so we put here the total of 6. Ammonium, we needed 1 unit of ammonium, so we write here 1 of ammonium, and then potassium. Potassium, in principle, we would write here 6 because that's the total that we need. But we go to this second stage and then we go back. We go to this stage and we see that we need 1 unit of phosphate and potassium. So we need to put here 1. So the remainder here would be 5. So we don't put here 6 of potassium nitrate because we need to put some potassium along with phosphorus. It's the only input for phosphorus. So the distribution would be 5 and 1, and the total would be 6. And then we complete, if required, potassium using potassium sulfate. Do we need to add potassium sulfate? No. And finally, we add magnesium as magnesium sulfate. We go here and we write 2. We have here 2 and 2. They are the same, so we write here 2. So these are the cells define the concentrations of these compounds. Ammonium nitrate 1, potassium nitrate 5, calcium nitrate 6, and so on. So this table is already telling us what are the concentrations of the different compounds. Here we have translated that into this other table. Here we see the chemical formulas and the milliequivalents per liter. Now we go to the table that we saw before and we put here the grams per equivalent for this compound. So we need 1 milliequivalent per liter of ammonium nitrate. We know that each equivalent of this compound weighs 80 grams. So we will need 80 grams per cubic meter, because this is the milliequivalent per liter is equal to equivalents per cubic meter. So we already know that we will need to add 80 grams of ammonium nitrate to each cubic meter of solution. And for the other cases will be the same. This is let's say, a general formula for a complete solution that would fit many crop species. In some cases, due to specific research, recipes have been developed for fertigation of different crops, like shown in this table, where the concentrations in milliequivalent per liters of different ions are shown. For instance, if we, in some cases, like in those marked with an asterisk, means that some phosphorus is put as basal fertilizer. For instance, melon on soil with basal phosphorus would require 9 milliequivalent per liter of nitrate, 0.8 of ammonium, 7 of potassium, and 4.5 of calcium. There is for some cases, there is a wide range in the possible concentrations of the different ions, but that depends. The use of this type of recipes depends on the specific research that has been performed for different crops in different areas, because this type of information cannot be translated easily to different environments, because the concentration, the best concentration in the soil solution for different nutrients will not be the same under different situations. It will depend, among other factors, of the evaporative demand.